Vanakkam. So, we will continue our engineering seismology course lecture. So, last class we have discussed about the interpretation of the seismic record. So, the seismic record what we record in the seismogram or seismoscope. Okay. So, basically it gives the waveform recording. Okay. This waveform record depends upon the energy released in the source and then how long it travels and what location it records, basically source, path and site. So, the combination of the effect is reflected in the waveform data. So, this waveform data only used to assess the energy released by the earthquake and the size of the earthquake and many more things which is useful for the engineering application. Okay. So, last class we discussed about the first part of the interpretation of seismic record. So, first of all how you can make a record perfect by applying a baseline correction if there is any drift in the earthquake recordings. Okay. Then followed by we have seen that after applying the baseline correction, so this record can be further identified that it is a recorded seismic events or it is a artificially generated some kind of vibration by machine or blasting kind of things. So, we have discussed how the several way we can identify the natural earthquake or artificially created blast vibration kind of things. So, with that we finish. Today we are going to talk about the next level of the interpretation, by particularly we are going to talk about the part of time domain parameters interpretation from the seismic record. So, as we have seen that during the seismic instrumentation part, the seismogram works basically a damped single degree freedom system component. So, where there is a mass and then there is a damping and then spring constant. So, when the stationary, so this part basically moves as a, so there is no movement here. Okay. So, when there is a displacement basically, okay, so then there is a relative movement of the ground. Okay. So, that basically takes care the your recording waveform details. Okay. So, this involves like the initial force m into u and the force of the damper, so which is like Cu and then force stiffness Ku. The opposite internal force due to the earthquake acceleration is mg. So, which can be easily basically understood by the single degree freedom wave equation. So, this is the form of equation which is solved to get a seismogram waveform recordings basically. Okay. So, this equation basically implies that the seismogram trace how much the acceleration or velocity or displacement is happening due to the particular vibration. So, that is what this earthquake record represents. So, we have seen that when the earthquake record represents, it may be like this. So, which does not have any baseline correction. So, once you apply a baseline correction, you can see the record like this, which is a perfect seismic record. Okay. So, up to that we learned in the last class how to identify the perfect seismic record. So, as we have know that this perfect seismic record may consist of the different composition of the waves such as a body wave, P wave and S wave, and also which the surface wave, Rayleigh wave and Love wave depends upon the where the seismometer is located and where the earthquakes is occurred. So, in general the range of frequency a seismological interest what we look for that. So, any vibration which is will be looking at like this a vibrating signal. So, basically the earth, okay, is a tide, okay, there is a earth tide means basically the vibrations caused due to the rotation of the earth. Okay, that kind of waves are called as a earth tide, which is generally having the frequency range of 0.001 hertz and below. Okay. So, which is called as a free oscillations. So, then the waves, the surface wave is the next frequency range which comes from generally 0.001 to 0.1 hertz. So, then the body wave again from 0.01 to about more than 10 close to 100 hertz. So, the range which is covered by the free oscillation frequency to the body wave frequency, middle of that range basically can be covered is the teleseismic events which can be generally recorded by the broadband seismogram. Okay. So, this is the event you can record. So, this means if you have instrument like this, okay, teleseismic event or broadband seismometer or very broadband seismometer, who could be able to record very long distance earthquake in your site. So, the another one we have seen that a local event which is basically recorded so by the regional seismic network, which I have discussed what is mean by regional network. Regional network is basically instrument which operated to measure earthquake happening within the region. Okay, so these are all the like the body wave predominantly can find in the the regional network, and surface wave and body wave composite predominantly find in the teleseismic or very broadband record. Okay. So, by looking at this type of wave, one can estimate a different magnitude which we have studied. So, like MS where you can use a surface wave, MB you can use a body wave, ML you can use a highest component of these three of them. Generally the S wave will be the highest component. So, the ML basically the S wave based magnitude estimate, which is like a local magnitude. So, we also studied about the magnitude saturation and then the moment magnitude, which is a function of the fault rupture, slip and stiffness of the fault. Okay. These are all the parameters which controls. So, these parameters will be reflected in the seismic record of the particular location or particular earthquake. So, the seismic record, as we have discussed, that there will be a typical, okay, so single component record or multiple component record. Okay. Multiple means like 3 components generally they use. So, the 3 component record basically implies that the one component they orient horizontal component towards a north direction. So, that means the north south is the one of the component, the another one is the perpendicular to that, the east west is the another direction, the third one will be the vertical component. So, this is the basically a typical earthquake. You can see the north south portion of the earthquake, where you can see there is a one type of wave arrival. So, possibly this will be the P wave, then followed by there is a S wave arrival, then followed by there is a small portion where you can see the surface wave. Okay. So, this is the north. Again the east west component, you can see basically the similar time it is recorded, but if you see the amplitude of the record, basically it has a different amplitude, it is not equal to this one. Okay. Then you can see the vertical component. Vertical, you can see that the P waves are very predominantly reflected. That is what we have seen when we have seen this animation recording the seismic station typical record. We have seen that the vertical waves are reflected. Okay. So, the P waves are well reflected in the vertical component of the record. So, that is what you can see. Then followed by the your S wave, then again there is a small surface wave component of that. So, this record may be was recorded station which is maybe the close to the epicenter location, maybe within a 100 or 200 kilometer. The close means it is a regional scale, 50 meter, 50 kilometer, 200 kilometer, 100 kilometer, these are all the regional scale record you can see. So, if you look at some of the large earthquake, okay, so where you can see that there is a distinguished difference between the velocity based record and acceleration based record. So, the previous one basically the velocity based record. This is actually the velocity sensor where the 3 component velocity has been recorded. So, this is basically from the seismograph. Okay. So, the next one axelograph, this is actually a 3 component record of the Pacomia Dam. So, recorded at San Francisco earthquake. So, we have discussed about the San Francisco earthquake. So, which is the largest earthquake in the San Francisco due to the transform boundary at San Diego place, okay, San Andreas fault. So, which was caused a very big damages, fire hazard, which I discussed. So, that earthquake actually it has a considerable amount of acceleration has been created against the gravity. So, this is the typical component of that you can see here. Basically the acceleration actually goes to 0.1, 0.5 to 0.5 g, 1 g, even some of the place you can see that it exceeding the 0.1 g. Okay. So, the horizontal instrumented are approximately parallel to the perpendicular, the horizon component of the rupture. So, where it shows the accelerations are. So, here they observed that the horizontal component of the instrument was actually perpendicular. Okay. So, the approximately parallel and perpendicular to the component of the rupture direction. So, because of that only you get a very high G value recorded in the this component, particularly the north. Okay, so north 14 component, you can see it is exceeding the G. So, the similarly for the south component. So, it was like there is a factor which controls although the rupture direction, rupture directivity. So, in case your seismic instrument oriented towards your north direction and the fault also rupture on the any north or east west direction. So, then you will have the record of high level of acceleration or velocity at a particular place. So, these are all the information one can have in the mind when they are processing and try to understand the earthquake. The same earthquake which is recorded in the same distance and elsewhere, it may not be oriented towards the fault directivity, but you will have the less acceleration or velocity value. Okay, so, this kind of directivity also influences the seismic record. So, this is the typical seismic record of the earthquake. Okay. So, you can see this earthquake actually the y axis basically acceleration or velocity. So, the x axis will be the time where that particular wave is arrived, how it is arrived. So, this data was taken from the old publications. So, where that Boer and Zabak. So, Boer is one of the well known world level seismologist, so who is working on USGS. Now he retired. So, I do have some kind of interaction with him, and he used to refer even some of my work for his research related activity. So, he is a well known seismologist basically. So, from his initial stage publication 1971, so those days publication this data was taken. So, as I said that the seismometer record velocity. Okay, so, the accelerometer record acceleration, but in general, so for the particular structural application, so we may need acceleration or velocity or displacement depends upon the what type of structure it is, what natural frequency of the structure. Okay, so that is taken into account. So, from one parameter if recorded, you can estimate all other parameters. As you know that, okay, so the acceleration can be integrated, you can get velocity, velocity can be integrated, you can get a displacement. So, if you want to displacement to the velocity, you can differentiate the velocity, you will get a acceleration. So, this is how any one parameter recorded will be converted into other parameters which is required for the your engineering application. So, this particular step is very important, because you know what record it is, from there you can convert to the record which you need for the engineering application. So, generally seismometers or seismoscope record a velocity, and accelerometer and accelerogram will record a acceleration versus time. So, how do you converted basically the earthquake record integration generally. So, if you have the earthquake record, okay, as we have said that the acceleration you can integrate and get the velocity, so record, no. So, like that one of the record, okay, so you should take, and you might have studied in the engineering this one that, so there is a integration and differentiation methods. Okay, so generally up to like B.Tech level or up to like UG level, we study this integration, differentiation basics and all, but we may not even really understand where these are really applicable. So, those kind of mathematical rules, okay, mathematical integration differentiations are used, okay. So, in the different engineering application, one of the engineering application in the engineering seismology is actually the integration is used to convert data from one, like acceleration to velocity, velocity to displacement. So, there are two type of integration rule they use, one is a trapezoidal rule and one the Simpson's rule. So, these are all the well known integration methods, generally we solve part of our course program. Those who are not studied engineering mathematics, maybe you will have some difficulty in what is this trapezoidal rule and Simpson rule. You can refer the website here, Wikipedia information. So, you no need to worry about that, how to solve this, as long as you are not going to process data yourself, but only you should know which data should be integrated, which data should be differentiated, and what method we should use. So, the integration generally the trapezoidal rules and Simpson rules are used. So, this is how the trapezoidal rule is taken, and this is how the Simpson rule they apply, and with using that you can convert the data from one form to other form. For example, integration of acceleration to get a velocity. So, this is the integration typical formula. Similarly, the velocity to displacement, this is the typical formula where you will get the your one acceleration to velocity, velocity to displacement. So, knowing this method, like you should use integration and what type of integration, and that is sufficient. Okay. So, nowadays there are a lot of software which is coded this. Okay. So, readily available to get your integration differentiation done. Only you should know how this works, that is enough, because our objective is not to teach you the processing of earthquake record or teach a mathematics behind the processing of earthquake record. Because of that, we are not going to in detail. Only you should know what you should know, what you should do, how you should do. That is sufficient for the knowledge of this particular part. So, similarly, the differentiation, you can do the numerical differentiation like first derivative. So, the forward difference and the central difference and backward difference. So, any of the three method can be used, any of the one method can be used to get a from displacement to velocity, velocity to acceleration. So, the more information about these methods can be obtained from this book or any standard. So, differentiation integration mathematics books which is taught in the first year of the engineering courses, or even sometime +2 level also people study this kind of formulas, okay, integration, differentiation kind of things, which will be sufficient. Once you integrate and differentiate, a particular type of waveform, okay, will be transformed to the other form of waveform. So, this is the typical earthquake, okay. So, where the all over earthquake east west component. So, each record, okay, each component of the record can have three type of plot. One is that acceleration time velocity plot, velocity time velocity plot, and displacement time velocity plot. So, this is basically the east west component. You can see the acceleration plot, where you can see the acceleration start with 0 and almost end with 0. Similarly, the velocity component, you can see how it goes and end with. So, displacement component, you can see how it goes and all. So, wherever that peak is there, you can get a higher displacement in this region. So, similarly, this is the same earthquake north south component, you can see here. So, where the acceleration, velocity and displacement. Okay. So, you can see even the displacement not attaining the 0 at the end of the record. Okay. So, similarly, this is the vertical component, where you can again get this one. You can even see the permanent sometime deformation in the vertical direction. So, this particular earthquake, you can see the permanent deformation in the vertical component. So, the each component of the data, okay, can be converted into other form like acceleration form, velocity form and displacement form. Okay. So, that is what we seen here. Okay. So, now, so you have the recorded earthquake data, which consists of the three component. Okay. So, two horizontal, one vertical. That three component again you can convert into the three form of data like acceleration time velocity, velocity time velocity and displacement time velocity. Okay. So, this is the first preliminary process you obtain. Once you convert all these data, okay, then you can get a what data you need for the engineering application. As I told you that, so when you are interpreting the data, there are two type of interpretation or two type of observation can be made to obtain a data. So, one observation is basically you look at your data, okay, and note down the values, that is like a time domain formation of the data. A time domain means like acceleration versus time, velocity versus time, displacement versus time, that is the time domain. So, by looking at those data, you get directly some parameters. Those parameters is called as a time domain parameters. Okay. So, the another one is you use this data and transform to other stage. Okay. So, that stage is basically is a frequency domain parameters, that your time velocity you will transform to the fast Fourier transformation, then you will get the Fourier spectrum. Okay. So, Fourier power spectrum, Fourier response spectrum, like that several form of spectrum you will get. That from that spectrum you derive some parameter, that is called as a frequency domain parameters. So, generally the time domain parameters, the first value they take from any record is actually the peak value of particular plot, like peak ground acceleration, peak ground velocity, peak ground displacement. So, this PGA, PGV and PGD is the short form which related respectively high and mid and low frequency of the ground motion component. So, that means if you are getting the acceleration value peak, so that will responsible for the high frequency component of the ground motion. if we are getting the velocity, it's a mid frequency of the component, and if we are getting the displacement at the low frequency component. So that means depends upon the your natural frequency of the structure, one can decide which parameter you should use or consider for estimating the seismic force. So if the structure, that is again the function of the your structure height and structure mass. So far the maximum recorded peak acceleration varies from 1g to 3g, which we have seen in that. The peak ground velocity reached so far reaching was 4 meter per second in the 1999 Chichi earthquake, Taiwan. So this is the highest level of PGA and PGV has been reported in the literature. So the peak ground acceleration, basically as we have seen that the each component of the data can be converted into 3 form. So this is the trickle form. So from here you will observe a peak. Peak means absolute value, no, not without sign. Among this, whichever is maximum, okay, that is actually the peak acceleration. Similarly, whichever is maximum is the peak velocity. Similarly, whichever is maximum is the peak displacement. Okay. So that you can directly see the waveform data and get the data. That data is useful for the several engineering applications. Okay. So if you look at the peak acceleration, a small particle attached to the earth during an earthquake will be moved back and forth rather irregularly. Okay, so this movement can described by the changing of position of the function of time by changing velocity as the or is changing the acceleration is the form. So in this moment the peak value basically is called as a peak acceleration, since any one of these described can be obtained from the any other. So like integration, differentiation. So we may choose whichever is most convenient is acceleration is chosen, because the building code prescribe how much horizontal force building should be able to withstand during an earthquake. So this force is related to the ground acceleration. The peak acceleration is the maximum acceleration experienced by a particle during a course of earthquake motion, okay, or the maximum waveform recorded in the seismogram. Okay, seismogram whatever it records. So the waveform whatever you are getting is a seismogram record is the your peak acceleration. So this peak acceleration also called as a peak horizontal acceleration, because as we have seen that each earthquake will have the 3 component, 2 horizontal, 1 vertical. So the peak ground means it is mean a maximum of that. So then when the knowledge was developed, there was a record from the rock as well as record from the ground surface. So then how do you differentiate that? That's why they call it as a, so the peak horizontal acceleration. So it may be recorded at rock, it may be recorded at ground, does not matter. So you can also call it as a peak ground motion, or you can also call it as a peak horizontal motion or peak horizontal acceleration, the PHA. Okay, generally the PHA means a recorded at a bedrock level, okay, or rock station. So PHA given component motion is simply the largest absolute value of the horizontal acceleration obtained from the accelerogram in the component. By taking a vector sum of the 2 orthogonal component, a maximum resultant PSHA, okay, so the direction will not be usually not coincide with the either measured component can be also obtained. So this PSHA can be also obtained as a the orthogonal component of the 2 horizontal component, that is way also you can have. So horizontal acceleration have commonly been used to describe the ground motion because their natural relationship with the inertial force. Indeed, the largest dynamic force induced certain type of structure like very stiff structures are closely related to PHA. So the scientist researcher found that so the damage is the function of the peak acceleration created, and these accelerations are basically related with the inertial force of the structure, that is why they use. So the vertical acceleration have received less attention in the earthquake engineering than horizontal acceleration, primarily because the margin safety against gravity induced by the static vertical force constructed work usually provide adequate resistance to the dynamic force induced by a vertical acceleration during earthquake. So the peak vertical acceleration is often assumed to be a 2/3 of the peak horizontal acceleration, which was suggested by the Newmark all in 1982, but now there was a observation and findings that this peak vertical acceleration changes to region, it never be a 2/3. The ratio of PVA and PHA however has more recently been observed to be quite variable, but generally greater than 2/3 near to the source to moderate to large earthquake and less than 2/3 long distance. That was the some of the observation has been made. So, India actually nobody was studied this kind of observations. So, one has to estimate how much we have the 2/3 or this one. So, when you look at this one, I need to also give you the idea about what we are talking basically. So, this is the typical earthquake. Okay, so, this may be the north south. Okay, so, this will be the east west component, then this one. So, here this is the east west. So, the peak value will be absolute peak value will be identified. For example, here this one. So, here if you go this, so this the highest will be the maybe this one. So, this value whichever among these two whichever is maximum can be called as a PGA or PHA, okay, one value, or you can also take both of them, find out a orthogonal value, that can be also called as a this one. So, they will specify which is the single of two component peak or orthogonal of two component. So, the orthogonal value generally less than the less than the highest one and maybe more than the this one. Okay. So, with this will be described for the this one in the particular record. So, the vertical component generally is whatever recorded data. So, then that peak you can take. Sometime in the absence of the recorded data, they used to take 2/3 of the value in olden days, but now the 2/3 value is not universal. So, it basically varies with the place to place. Okay. So, that is what we found in the many of the research. So, these peak acceleration values are very sensitive to the high frequency of the data. So, if you are constructing the high frequency structures, then you should consider peak ground acceleration or peak horizontal acceleration for the design parameters. So, the next one is basically a peak velocity. The peak horizontal velocity or peak ground velocity is another useful parameter for characterization of the ground motion amplitude. Since the velocity is less sensitive to the high frequency component, the ground motion, the PHV is more likely to PHA to characterize the ground motion amplitude accurately for intermediate frequencies. So, generally when the intermediate frequency range, okay, will show the high peak velocity or peak horizontal. So, the structure or facility that is sensitive to the loading in the intermediate frequency range, such as a tall structure, flexible building, bridges, the PHV or velocity based design has to be done. The velocity parameter should be taken as a input for designing these kind of structures. So, the PHV has also been correlated to the earthquake intensity by the several researchers, where you can see the how the particular structures are got damage, how much percentage got damage with respect to PHV angle. So, whenever you have the this kind of tall structure, flexible building, bridges and all, your acceleration is basically meaningless. You have to consider a velocity data and the peak horizontal velocity for the design. So, the another one is the peak displacement. So, the peak displacements are usually associated with the lower frequency component of the earthquake. So, they are however often difficult to determine accurately due to the signal processing error in the filtering and integration of acceleration and due to the long period noise. Okay. As a result, peak displacement less commonly used. Okay, peak displacement less commonly used to measure a ground motion than a peak acceleration or peak velocity. Okay. So, this is very less used in the engineering, but nowadays there is a displacement based approach. Okay. So, where they design, where they consider the displacement parameters for the design of those kind of structures, particularly the low frequency structures where the peak displacement is used as a parameter to design. So, we have seen so far. So, we have taken the typical acceleration time history of the data or typical record okay, 3 component record. So it has a 2 horizontal component, okay, so southwest direction, east west direction, 1 vertical component, and each component you can convert from one form of data to other form of data. For example, the seismometer record as a velocity. You can convert the velocity to the displacement by integration, and you can convert velocity to acceleration by differentiation. Okay. So you convert that data will be useful for engineering application. Once you converted this kind of 3 form of data of the single component, so then you can consider the 3 after converting the 3 form of the 3 component data, like we have the 9 component, okay, 9 data you will have for a single earthquake at a single station. So then you among these 2 horizontal component, okay, so you will have 2 horizontal component. So these 2 horizontal component has basically 3 form. So you can consider acceleration where is the peak, velocity where is the peak. Then you can report what is the peak horizontal acceleration, peak ground acceleration. Similarly, peak horizontal velocity or peak ground velocity. We have seen that in order to differentiate easily the bedrock and the surface. So if it written at the horizontal, it is preferably shows it as a bedrock record. If it is written as a peak ground, it may be recorded at a soil site, okay, on the ground. Okay, that is the way you can differentiate. So these data, so we have seen that the accelerations are sensitive to the high frequency range, so that the high frequency structure, the frequency which has the structure which has a natural frequency higher, okay, that has to be designed by considering the acceleration. The structure which has a medium frequency, okay, that has to be designed by considering the velocity, peak velocity or velocity component of the data, and the structure which is sensitive to the low frequency range need to be designed by the displacement. So we also seen that the velocity is basically 2/3 of the acceleration in general, but however the recently this is not a uniform value, it varies region to region, which has to be found out and used in the practical design application rather than assuming the 2/3. Okay. So displacement generally not so much used for the design, as it is getting accurate displacement or peak displacement is may not be possible due to signal processing error and filtering, and then there is a long term noise also will affect the quality of the data. So with this we will close this class. So next class we will see what are the other parameters, time domain parameter we can interpret from the earthquake record. So thank you very much for watching this video. So we look forward on the next class.